Alright guys, today we're going to be doing Evasion Shellcode Task 4, Intro to Shellcode. Alright, so shellcode is a set of crafted malicious code instructions that tell the vulnerable program to run additional functions, and in most cases provide access to a system shell or create a reverse shell. Once the shellcode is injected into the process and executes by vulnerable software or program, it modifies the code run flow to update registers and functions of the program to execute the attacker's code. It is generally written in assembly language and translated into hexadecimal opcodes, operational codes. Writing unique and custom shellcode helps in invading AV software significantly. But writing a custom shellcode requires excellent knowledge and skill in dealing with assembly language, which is not easy to learn. A simple shellcode. In order to craft our own shellcode, a set of skills is required. A decent understanding of the x84 and x64 CPU architectures, assembly language, strong knowledge of programming language such as C, familiar with Linux and Windows operating systems. To generate our own shellcode, we need to write and extract bytes from the assembler language code, machine code. For this task, we will be using the attack box to create a sample shellcode for Linux that writes the string thimrocks. The following assembly code uses two main functions. System write function, syswrite, to print out a string we choose, and the sysexit function to terminate the execution of the program. To call those functions, we will use the syscall. A syscall is a way in which a program requests the kernel to do something. In this case, we will request the kernel to write a string to our screen and exit the program. Each operating system has a different calling convention regarding syscall, meaning that to use the write in Linux, you will probably use a different syscall than the one you'd use in Windows. For x64 Linux, you can call the needed function from the kernel by setting up the following values. So this is the value, syscall write, unsign, okay. The table tells us what values we'll need to set in different processor registers to call the syswrite and sysexit function using the syscall. For 64-bit Linux, the RAX register is used to indicate the function in the kernel we wish to call. Setting RAX to 0x1 makes the kernel execute syswrite, and setting RAX to 0x3c will make the kernel execute sysexit. Each of the two functions require some parameters to work, which can be set through the RDI, RSI, and RDX registers. You can find a complete reference of the available x64 Linux syscalls here. For syswrite, the first parameter sent through the RDI is the file descriptor to write to. The second parameter in the RSI is a pointer to the string we want to print. Okay, and the third in the RDX is the size of the string to print. Okay, for sysexit, RDI needs to be set to the exit code for the program. Okay, we will use the code 0, which means the program exited successfully. Copy the following code into your attack box in a file called thimasm. Okay. All right, so we'll just do that real quick. I got my attack box here. I was kind of running through the list last time, so hopefully I don't get lost. Let's go to my desktop, and I should have a shellcode folder here, hopefully. Kernel exploits. No, that's not it. All right, oh, here it is, shellcode. All right, cool. So I think I've already done that. Global start, section.text, sort, jump message, subject message, move RAX right here. We've set this value for the attribute for the for the parameter, and then RDI. Set this value. All right. And then RSI is right here. RSI is a pointer to the string we want to print. We are popping into RSI. Now we have the address of them rocks. Okay, and then the RDX is the size of the string pointer. And then we do our syscall move just to exit. All right, so let's understand what's going on here. Let's explain the ASM code a bit more. First, our message string is stored at the end of the .text section. Okay, so here's the .text section. Since we need a pointer to that message to print it, we will jump to the call instructions before the message itself. When the call go back is executed, the address of the next instructions after the call will be pushed into the stack, which corresponds to where our message is. Okay, so this will be pushed to the stack. Note that the ODHOAH at the end of the message, it's right here, is the binary equivalent of R in /n. Next, the program starts the go back routine and prepares the required register for our first syswrite function. We're going, okay, so we have, it's even numbered here, right? So let's jump to this message. And then 2 here, we're going back since we used the call. That means the return address, which is in this case the address of them rock, is pushed into the stack. Okay, so this is what we jump to. So we start here, we jump to this, we push this to the stack, right? Next, the program will start the go back routine and prepare the required registers for our first syswrite function. Okay, so then we're starting the syswrite function. So we're popping into the RSI. Now we have the address. Okay. So we specify the syswrite function by storing a 1 in the RAX register. Okay, so the RAX is right here. So we store a 1 there for the syswrite. That's why we have the 1 there. Okay. We next set the RDI to 1 to print out the string to the user's console. Okay, so then we set that to 1 so we can print out the string to the user's consoles. And then pop RSI, we pop a pointer to our string, which was pushed when we called go back and stored it into the RSI. So we pop into the RSI now that we have the address. Okay, so then we pop into the RSI to the pointer to the string that was stored, right? So we push it into the stack and then we pop into the pointer of our string, which is pushed. We did the callback. Okay, I just need to understand it. With the syscall instructions, we execute the syswrite function with the value we prepared. So then we execute the syswrite function with the value we prepared, and syswrite. For the next part, we do the same to the sys exit function. So we have the 03C right here into the register and call the syscall function to exit the program. Next, we compile and link the ASM code to create an x64 Linux executable and finally execute the program. All right, so then here we're compiling it, and then after we compile it, we run it, and then it just prints that message out. So if we do this on our own machine, it should work, right? So I have it saved here. I'm just gonna close it out. I'm gonna open up a terminal here, and then we'll test this out, right? So I'm gonna do this command. I'm just gonna paste that in. Yeah, okay, cool. So we compiled it, and then here we're going to run this portion, and then I could read through this. So we use the NASM command to compile the ASM file, specifying the -f ELF64 option to indicate we are compiling for 64-bit Linux. Notice that as a result, we obtain a .o file, which contains object code. Right, that makes sense because that's them.o, which needs to be linked in order to be a working executable. The ld command is used to link the object and obtain the final executable. All right, so we have to link it, and then we get our final executable. The -o option is used to specify the name of the output executable file. So here, actually this is, so the name of the executable file is thm. Now that we have the compiled ASM program, let's execute the shellcode with the objdump command by dumping the text.text section into text section of the compiled binary. So if you use this command, it will dump the text section of the compiled binary. And when we do that, we can see more details. Okay, this is kind of starting to make sense to me. Huh. All right, so I'm gonna run that. I just want to see that, and I want to see that work. So let me grab that. Come over here. Whoa, what's going on here? All right, paste this in. Oh, cool. So that's it's executable now. So next we'll run this command. I think I might have to chmod it though to run it. Hey, it works. All right. All right. So next we're gonna jump. We're gonna dump the text section of that executable. And when we do that, let me just expand this. We get this, which kind of looks like what we were looking at earlier, except we got maybe some hex values here. So let's learn more about what's going on here. Now we need to extract the hex values from the above output. To do that, we'll use the obcopy to dump the .text section into a new file called the them text in a binary format as followed. So obcopy -j.text -o binary dim text. Okay, let me copy that, put it over here. All right, and now we should have a text file there, and it's right here. I'm guessing we're going to cut that out. The dim.text contains our shellcode in binary format. So to be able to use it, we need to convert it to hex first. Okay, so we're going to use another command to convert it to hex. The xxd command has a -i option that will output the binary file into a C string directly. Okay, so we're gonna take this binary file that, like machines can interpret or understand at least, and then we're going to output into C so we can understand what the heck it's doing. Finally, we have it, a formatted shellcode from our assembly, ASM assembly that was fun. As we see, dedication and skill are required to generate shellcode for your work. To confirm that the extracted shellcode works as expected, we can execute our shellcode and inject it into a C program. Okay. Okay, so this is the same. This is the same as that, except so let me do that. Let me follow along here. I'm gonna make sure I don't fall behind. Okay, so next I'm gonna put this in here so we can get the C version of it. And there it is right there. Then we compile and execute as follows. Okay, so then I take this. So when I do this, it should work. Oh no, it didn't. Oh, we're using GCC. What's going on here? Oh, do we have to save this? Oh wait, never mind. Okay, so we have that C code, but as we see here, it's just we have a few other things include stud.h, int main, int arg, and character. I don't really know what that means, but and void message return 0. Boy, I wish I understood C right now. I know C sharp, but not C, so I'm just a little confused. Then we compile it as followed. So are we compiling dim.text? Is that what we're compiling? What are they compiling here? GCC, all dimc. Oh, this is a dimc. Okay. Right, so it's like a C file. Let me see if I. Oh wait, let me go up a little bit. Yeah, so this is dim text. So we got dim text. Before that, it was dim text. Okay, so I think if I copy this and then I make a new file and I name it dimc, maybe it'll work. Let's give it a shot. Usually I pause the video when I do this stuff, but I have a feeling it's gonna work, so I thought I'd give it a shot here. If it doesn't, I'll have to pause it. All right, so that kind of worked. All right, so that should have created another file here, right? So, okay, there's MC, and then the output it another executable. So then when we run it, I don't even know which it's going to run one of those executables. So I think they're both named the same. Yeah, so it worked. Now it worked. Note that we compiled the C program by disabling the INX protection, which may prevent us from executing the code correctly in the data segment or stack. So it looks like INX would have been some type of security protection to prevent us from altering the stack like that. Understanding shellcode and how they are created is essential for the following tasks, especially when dealing with encrypting and encoding the shellcode. Modify your C program to execute the following shellcode. What's the flag? Okay, so this looks like it's already in a hexadecimal, like hex format, kind of like this. So all we need to do is pretty much put this here, do what we did here to take that C and just like how'd you say this? Compile it and compile it to an actual C program and then to an executable. So let's do that. So I'm gonna take this, and I think all we need is up to the curly bracket. Copy that. Come over here. Pretty much do the same thing. So this file right here, this was the before we start altering it, this was the dim text file, right? So I go here, my dim text file, and it doesn't want to open. So then I just, gosh, let's see, subline, where are you? Where are you when I need you? Here you are. All right, so cool. I have it still open in subline. You could open it with whatever you want. You could open it with nano or because nano's the best or whatever you choose to open it with. But I'm gonna replace this curly bracket all the way to this curly bracket. So I'm just gonna delete that and then I'm gonna paste that in. Okay, and then it's not gonna work, of course. So let's see here. Let me scroll down a little bit. Let me grab this schnips. All right, so I'm gonna use magic to reverse what I just did. So Control Z as in Zulu, and it's going to revert what I just deleted. That is honestly a lifesaver. I've used it so many times. Control Z. I've accidentally deleted something. I'm like, oh no, you know, and I'd use Control Z and I get it back. Okay, life tip. All right, guys. So let me go back to this. We'll just take everything from the semicolon to the equal sign. I'm going to copy this. I'm going to put this in Notepad to see if it's actually copying it or if somehow something funky is going on here. So it is copying it. Good. Now I'm come over here and I'm going to just replace everything from that to that. I'm just going to paste that in and then just cross my fingers and hope that it actually does it. It actually like copies it over. Yeah, see, it's not copying it. What's going on here? All right, let me just save this. I don't know. Oh, snaps. All right, so let me save this and what should we call this? Dim.text. Dim.text actually spelling out text. I think that's a good idea. Dim.text.text. As long as I know which file it is, I think we should be fine. So I'm gonna save that. Go to the location of this file, which I have on my computer. I don't know if I'm having an issue with Kali right now, or I'm having issues pasting things. But let me try to go here. So I'm gonna pause this while I get this all done. All right, I have it here. Here's the text file. I'm gonna drop it. And there it is there. For some reason, I was having issues copying it. No worries. I'm just gonna open it. And then there's the hex of an actual C program we can use. I'm gonna come back over here. Oh, this is a subline, so I can just come in here and just alter it. Just come in here and alter this real quick. Paste that in there. That looks good. No, that doesn't look good because I have two equal signs. I think that's wrong. So hold on, let me Control Z. All right, and I'm just gonna delete this first, and then I'll copy it. No, it is good because there's a curly bracket right above it, right here. All right, I was just like, wait, what's going on here? All right, I'm gonna save this. I'm really hoping this works because if not, I don't know. All right, grab this, copy that. I'm going to now compile my file. And I always like to save it again just because, I don't know. Run this, should overwrite whatever we have. Oh, dang it, I got an error. What's going on here? Unexpected character. Right there. All right, let me look at it. Oh, snaps. There's two equal signs. One of those is gonna have to go. All right, that should be good. See, does this tell me if I have an error? Nope. All right, cool. So now I'm gonna run it. All right, that worked. And then now we're going to run our executable here, our shellcode, proper terms here. And it got me my flag. Sweet. And I kind of understand this. It's like, I'm just hanging in there. Pretty great stuff. Copy that. Come over here. And as always, I'm gonna put this flag in the comments, or actually in the description. There it is. All right, guys. So I hope you guys didn't get lost. I tried to reread it, so I can understand it. But I guess there's a lot going on here. But they do list out the process, right? So let's jump to the message. They jump to the message. This is the message. We are going back since we used the call. That means the return address, which is in this case the address of the dimrock/r/in, is pushed into the stack, and then that's the message there. Then, that's all because of go back, right? And then after that, then you have the sys write starting, and then now we're popping into the RSI, which if we remember, the second parameter in the RSI is the pointer to the string we want to print. And now we have the address of dimrock. So now that we have that address and we've pushed it to the stack, now we can execute it. And then that's essentially what happens. And then right here is a sys exit. And you're hearing this all from a guy who just learned this like 30 minutes ago. Anyhow, so that's task 4. It's getting late. I got work tomorrow, so I'm gonna head to sleep. And I will probably make a task 5 and task 7. Let me take a quick look at a gander at it, see how difficult this is. This doesn't look too difficult. It looks like something we just learned, right? We just did this. This doesn't, yeah, and then they compile it and then they run it, and then you get a calculator. Just true malware, because nobody wants to do math. All right, and then here, generate shellcode from exe files. All right, so earlier we were doing it from, what is this? Workflow from C. That we can execute, and then now we're going to do it with exe file, which probably isn't going to be too much difference besides when we compile it, it has to be an exe format. So, that doesn't seem too difficult. I think we can get through this, guys. And this looks really interesting. This is going to be for stage payloads. Wow, that sounds really cool. And we're using Metasploit. So, this probably isn't going to be too difficult because Metasploit's going to do all the work for us. I mean, hopefully. I don't know if it is or not. Yeah, it looks like Metasploit's doing pretty much all the heavy lifting here. So that doesn't look too difficult. Easy, right? I say that until I'm doing it, my brain explodes. Anyhow, hope you guys have a good one. Please like and subscribe. Danny out.